Hello students, and welcome back to another geometry video. You know what to do. Pause the video, try this problem in your notes, and then unpause it to do it with me. Alrighty, we are asked to find the area of the regular polygon. Regular is important. We know from our formula sheet that we got in class that the area of a regular polygon is equal to 1/2 times the apothem times the number of sides times the side length. Do you need all those little asterisks in there? No, I like to highlight those just so that we know what to type in our calculator. But we are taking 1/2 times the A stands for apothem, the N stands for number of sides, and the S stands for the side length. So we have 1/2 of, what is our apothem? Our apothem goes from the center of the polygon out to the edge such that it makes a right angle. So that right angle is super important. So our apothem is 2 times the square root of 3. The number of sides, what kind of shape is this? Good job. It is a triangle, so that we have 3 sides. And the side length is how long the whole side is, and we have right here, this 12 is labeling the entire length of that side, so we have 12. We are going to take our handy-dandy calculator, and we're going to type in 1/2 times 2 times the square root of 3 times, if I can work my fingers correctly, times 3 times 12, and we will get approximately 62.353. This problem didn't say what to round to, so we get to decide. I'm deciding that I want the nearest tenth. The tenth is the first number after the decimal place, so this will stay 62 point. Ooh, will it stay 3 or will it go up to a 4? We need to examine the number after the 3, which is 5. 5 is big enough that that 3 goes up to a 4. And that is our area of the regular polygon. What are our units? They didn't give us units, so we just write units. But are these one-dimensional units? Are these two-dimensional units? These are two-dimensional units. These are square units. Anytime we're talking about area, we are talking about 2 dimensions, square units. Fantastic. Alrighty. All right, and that was a good review of the last lesson. Now let's move on to what we have for this video. We will be looking at 11.4, 3-dimensional figures. Ho-ho, area was 2 dimensions. So we learned about circumference, we've learned about area of circles, we've learned about area of polygons, we've looked at 1 and 2 dimensions. Now it's time for 3 dimensions. So throughout this video, we are going to learn what 3-dimensional shapes look like. We're going to talk about different shapes. We're going to name different shapes. So we're going to classify them, 3-dimensional shapes. We're also going to look at their cross-sections and revolutions. These are fun. The classifications are fun. They're not too bad. They're not too difficult once you get the hang of them. The cross-sections takes a little bit of brain power, but it's so cool. Oh my goodness. I love bringing food in and like cutting up the food to see the different cross-sections. Oh, it's great. And then revolutions are very interesting. You're going to use them in integral calculus, calculus 2, when I'm sure you take that, because you can, if you want to. So yeah, we're going to look at 3 things today: classifying, cross-sections, and revolutions. So let's jump right into it. First, we're going to start with our vocab and classifying solids. A 3-dimensional figure, or solid, whatever you want to call it, is bounded by flat or curved surfaces, they could be curved, that enclose a single region of space. So when we talk about 3 dimensions, we're talking about enclosing space. Like the area, okay, that's just a surface. You're not enclosing any space. But with 3-dimensional figures, we are enclosing some amount of space. All right. A polyhedron is a solid that is bounded by polygons, so hence polyhedron, polygons called faces. So the faces are the polygons that you connect to make up the 3D shape. So in this case, you have rectangles on the top. This top is a rectangle. You have this side that is also a rectangle. But then you have this shape on, like, I don't know, the bottom or the side closest to us. What kind of shape is that? Oh, do we remember from chapter 7? It is a trapezoid. So it doesn't all have to be rectangles, it doesn't all have to be squares. You could have trapezoids, you could have triangles, you could have hexagons, you could have all sorts of polygons. But a polyhedron specifically is bounded by polygons, which we call faces. The edge of a polyhedron is a line segment formed by the intersection of two faces. So anywhere two of the polygons intersect, you're going to have an edge. So the edges are kind of like the lines, like the one-dimensional lines. The polygons are 2 dimensions, of course. Alrighty. A vertex of a polyhedron is a point where 3 or more edges meet. So basically all of the corners are your vertices. Singular is vertex, plural, or excuse, yeah, singular is vertex, plural is vertices. Now, one distinction I want to make, when we talked about 3-dimensional figures, it said flat or curved. But now you're coming in here saying polygons. Polygons can't have curved surfaces. So 3-dimensional figures can have flat or curved shapes in them. Polyhedrons specifically do not have curves, and we're going to talk about that on the next slide. One more thing, the plural of polyhedron is polyhedra or polyhedrons. So you'll hear it both ways. I like polyhedra because it sounds kind of fancy, but you'll hear both words. Doesn't matter which one you use. Both are correct. All right. Moving on to our next slide, I want to highlight a little bit more what I said about no curves. For polyhedra, there are no curves. Only polygons, straight edges, 3 or more sides. But there are other shapes that are not polyhedra, and they are allowed to have curves. So the non-polyhedra have all the curves, or circular shapes, however you'd like to describe it. But polyhedra should be only polygons. No curves for our polyhedron. So that's how you'll know if it ever asks you, if a problem ever asks you, is this a polyhedron? If it's got curves, no sir. And that is a good segue into our first example. Nope, just kidding, sorry. Our first example is on the next slide. First, there are 2 types of polyhedra. First, you have prisms, and second, you have pyramids. What is the difference? Can you tell just by looking at them? The one on the left is a prism, the one on the right is a pyramid. Can you tell me what's the difference between a pentagon and a pyramid? Maybe pause the video and think about it if you'd like. Unpause it and we will explain. A prism has 2 matching bases. So see this pentagon on the top here, and then you see the pentagon on the bottom here. So you should have 2 matching bases connected with rectangles. So if we highlight, we have a rectangle here and a rectangle here, a rectangle on the side over here, the rectangle on the front, and then another rectangle on the side over here. They kind of look like squares. Maybe they are squares, maybe they're not rectangles. But square is a type of rectangle, right? So rectangle just covers it all. So a prism has 2 bases that are identical, connected by rectangles. A pyramid, on the other hand, has 1 base. In this case, it's a triangle, but you can have whatever base you want. It has 1 base, and all of the vertices of the base come up to a single point. So pyramids will have a single point, and prisms will have 2 faces connected with rectangles. One thing to note, kind of cool, important detail, you probably already figured, the 2 bases of a prism are congruent polygons, the same polygon, in parallel planes. What does in parallel planes mean? Well, if you remember from chapter 1, parallel planes do not intersect. These planes are not parallel because they would intersect. If the bases of your prism are not parallel, then the rectangles on one side are going to be bigger than the rectangles on the other side. The rectangles should be the same length. You should have the same height all the way through the prism. So if your base is tilted, the height isn't consistent from one side to the other. So your bases should be in parallel planes. That way they'll never cross, and the height will be exactly the same all the way around the shape. All right, cool. We're going to practice this on the next slide, but I want to let you know that we name shapes, both prisms and pyramids, with their bases. So for example, on the left, the bases are pentagons, so we call it a pentagonal prism or a pentagonal prism. Doesn't matter which way you say it. On the right, the base is a triangle, so we call this a triangular pyramid. All right, let's have some more practice with naming shapes. Here we are in example 1, classifying solids. First, we are going to tell whether each shape or each solid is a polyhedron. And second, if it is, we are going to name the polyhedron. So first, let's look at A, the picture in part A. Is this a polyhedron? What did it mean to be a polyhedron? No curves, only polygons for our faces. Does this have any curves? No, it does not. It is a polyhedron, so yes, it is a polyhedron. Now we need to name it. So first we ask ourselves, is this a prism or is this a pyramid? Does everything come up to one single point? No. So it's probably a prism. Let's look and make sure. It needs to have 2 matching bases. Where would the, connected by rectangles, where would those bases be? Well, they've actually highlighted them for you, and let me get another color so that I highlight them as well. Let's do blue. If we look at the ends here, these are 2 identical shapes. And what are those shapes? I want you to think about it for a second. What do these red markings mean? We have congruent sides. The left and the right are congruent. The top and the bottom are congruent for both of these. And they gave you a right angle box in the corner. That is enough information, excuse me, to know that these are rectangles. Rectangles. And how do we name a polyhedron? We name it using the base. So this is a rectangular prism. I'm highlighting rectangular in blue along with the bases so that you remember we name the shapes with their bases. So because the bases are rectangles, this is a rectangular prism. If these bases had been triangles, we would have called it a triangular prism. All right. Next, let us look at part B. Is this a polyhedron? Do we see any curves? No, I only see straight edges, so this is another yes, it is a polyhedron. And what type? Next thing to ask is it a prism or is it a pyramid? See how it all comes up to one point at the top? That's an easy way for me to tell that it is indeed a pyramid. Now, could it come together in points at the bottom? Does it have to be at the top? It could be at the bottom as well. If it were at the bottom, this would still be a pyramid. It doesn't matter what the orientation of it is, as long as the base, the vertices of the base all come up to one vertex up at the top. Well, at the top, at one area, as long as they all come to one point. That point could be on the side, that point could be on the bottom, that point could be on the left, it doesn't matter, as long as they come to a point. So, this is a pyramid, but what type of pyramid? Let me get a different color. We'll do green this time. Remember, to name a polyhedron, we need to look at the base. So the base is opposite the point. Could be at the top, could be at the bottom. But the base is opposite that point at the top. So I'm going to highlight it for you here. Whoa! What is that shape? How many sides did it have? 1, 2, 3, 4, 5, 6. 6 sides. That makes it a hexagon. So this is a hexagonal, however you want to say it, pyramid. Period. All right, fantastic. Lastly, let's look at part C. Is this a polyhedron? Does it have any curves? Yes, look at that big old circle right up at the top. So this is not a polyhedron. No, not a polyhedron. Not a polyhedron. What kind of shape is it if it's not a polyhedron? Can you guess? Have you seen this shape before? This is a cone. We are going to learn about cones. We're going to learn about polyhedrons, and then we're going to learn about cones, spheres, cylinders, all of it. Chapter 11 is a big, big bundle of fun where we're going to learn about every shape, almost every shape. So this is not a polyhedron, it is a cone. All right, let's check and make sure that we are correct. Formed by polygons, so it is a polyhedron. Rectangles, or bases are rectangles, so rectangular prism. Polygons, polyhedron. Base is a hexagon, so it is a hexagonal pyramid. The cone has a curved surface. Curves are the key, so it is not a polyhedron. Awesome. Hooray, we were correct. Okay, let's move on to our next concept for today, cross sections. What the heck do we mean by cross sections? What we are saying when we say cross section is if I take a water bottle and I cut it in half, and then I look at where I have cut, what shape will it look like? What you have cut. When I cut it, I'm not looking at the three-dimensional shape I get after I cut it. I'm looking at the two-dimensional shape after I have cut it. So pretend this were longer and I cut off the bottom. What is the shape on the bottom of this water bottle? It's a circle. So the cross section of, this would be almost a cylinder. It's higher at the top, lower at the bottom. This would almost be a cylinder. So if we take a horizontal cross section of this cylinder, we would get a circle. But you can take a cross section of any shape. You could take a cross section of a Reese's peanut butter cup, or a Skittle, or a, I don't know why I'm thinking about candy right now. You can take the cross section of anything. In this example that they're giving right here, this isn't the example that we will do. We're going to try some problems on our own in a moment. But first, we are looking at cubes. So the blue shape that we're looking at here, the three-dimensional shape, is the cube. And then they have this yellowish plane that is slicing through the solid. So you can think of it as like a big sheet that's cutting through the shape. So this yellowish color is a plane that we're using to cut, and the purple section in the middle is the cross section that we get after we have done the cutting. So, the intersection of the plane and the solid is called the cross section. So the cross section is only 2 dimensions. It will be a 2-dimensional shape that you can draw on paper. It won't be a 3-dimensional shape that you need, to come out of the paper to draw. All right, if we look here in the first example that they give, we take a cube and we just slice it perfectly horizontally, parallel to the base of the cube. Well, what shape, what 2-dimensional shape is the base of a cube? A cube is just a ton of squares put together, right? All the bases of a cube are squares. So if we slice the cube parallel to the base, it is also going to be a square. And that's what it says right here, is that if you cut it parallel to the bottom, perfectly horizontally, you will get a square. Okay. What if we cut it at an angle, though? What if we don't go perfectly horizontally? What if we come in at a diagonal? What if we start at like the top left corner of the cube and then go down to like the bottom right corner of the cube? Then what will we get? Well, these two sides, the ones that I've highlighted right here, these are going to be congruent, right? The edges of all the cubes have to be the same length because it's a ton of squares put together, and squares have the same side length. But these sides are going to be longer because they connect, right? They go through the square. This side is going to be shorter than this side. You know how I know? Because that's the hypotenuse. The squiggly line would be a hypotenuse across from this right angle. So it would have to be longer, right? The hypotenuse is always the longest side. So the two squiggly lines I've drawn are going to be longer than the two other sides, and that makes it a rectangle. It's only a square if every single side is the same. So if we cut it diagonally, we're going to get a rectangle. All right. And the last example they give is, what if we just cut off the corner of the cube? Actually, I have a Kleenex box here. This is kind of cubular. What if I just cut off, I just snip the corner of this Kleenex box off? What shape will we get on the corner? Well, you're going to get a triangle. You're going to get a triangle. And depending on what angle you go at, it might be an isosceles triangle. It might be a scalene triangle. It might be a right triangle. It totally depends on the angle at which you cut the cube, you cut the corner of the cube off. But if you cut the corner, you are going to get a triangle. All right, I know picturing this in your head can be a little difficult at first, but we're going to try it with some other shapes. So here is our second example. We are going to describe cross sections using the blue shape is the three-dimensional shape. The yellow plane is what we're using to slice, and then they have highlighted the cross section in purple for us. So first, let's identify, in part A, let's identify what three-dimensional shape is this that we're looking at. What are the bases? Let me see the bases. I'm going to highlight them. The bases have 1, 2, 3, 4, 5, 6 sides. So this is a hexagonal prism or pyramid. Prism, because it doesn't come to a point. This is a hexagonal prism. So if you can picture that in your head, think of like a cylinder standing up, but the bottom is a hexagon and the top is a hexagon. Instead of being smooth all the way around, you have a hexagon on top and a hexagon on the bottom, and you connect them with lines coming down. So this is like a hexagonal prism that we've put on its side, basically. And we are cutting it perfectly parallel to the base. Anytime we cut parallel to the base, the cross section is going to be the same as the base. Think of a loaf of bread. A loaf of bread has this kind of shape-ish. Well, and then it's 3 dimensions. So you have, you know, this kind of shape. I'm not an artist. But you have this kind of shape. But a slice of bread looks exactly like the base of the bread, because we're cutting parallel to the base of the bread. Anyways, so if we cut parallel to the hexagonal base, the cross section will be a hexagon. And it is. If you look at the purple shape that they've highlighted right here, the purple shape is indeed a hexagon. Okay, next, let's look at B. What is the blue shape? What's the three-dimensional shape we're looking at? This is a pyramid. I know because it comes to a point. What is the base of this pyramid? It is a 1, 2, 3-sided shape. It is a triangle. This is a triangular pyramid. And again, it looks like we're cutting parallel to the base. In part A, the bases were standing on the ends, but on part B, the base is sitting on the bottom. So when we say parallel to the base, it could be up and down, it could be horizontal. It depends on the orientation of the bases. In part B, the base is at the bottom of the shape, so we are cutting horizontally, and we will get a shape similar, like in chapter 8, similar to the base of our shape, which is a triangle. So part B is a triangle. Okay, part C. Ooh, what is the blue shape? What's the three-dimensional shape? It is a cylinder, so we can think of our cylinder example from before. But now, we're not cutting it horizontally. We're cutting the cylinder vertically. What shape are we going to get if we cut it vertically? Well, the top will be a straight line. The bottom will be a straight line. What will you have on the sides if you cut it straight down? Oh, you'll have like the sides of the cylinder. So those will also be straight sides, just vertical. Huh. What do 2 flat sides and 2 vertical sides make together? They make a rectangle. Is it a rectangle or a square? In our case, it's a rectangle. Could it be a square? It could, if the rectangle were a different height. It could be a square. But you are guaranteed for it to be a rectangle no matter what the shape of the cylinder, the width or the height. You will always get some form of rectangle. And remember, a square is just a specific type of rectangle. Awesome. All right, part D. What's the blue three-dimensional shape? It is a cone. What is the base of a cone? It's a circle. So this is kind of like a circular pyramid, only pyramids have triangle faces, and a cone doesn't have faces because it's a smooth surface. So it's not a pyramid, it's a cone. But again, look, we're cutting parallel to the base of this cone. So what is the base of the cone? It's a circle. If we cut parallel, our cross-section is going to be the same as the base. So for part D, we have a circle. A circle for our cross-section. And you can see if I highlight the purple shape they have drawn, that is a circle. Awesome. All right, part E. Ooh, what is the blue three-dimensional shape called? We haven't seen this one yet. It is a sphere. A sphere is perfectly circular all the way around. So if we take a knife or a plane and we cut it straight down the top, that's what this yellow plane is doing. It's going right down the middle through the top of the sphere. When you open the sphere, think of like a coconut in the movies when they cut open a coconut. What is the two-dimensional shape when you open that coconut? It is also, whoops, pardon me, it is also going to be a circle. Huh, cool. Now let me ask you this. Is it possible to cut the sphere in some other different sort of way that won't get you a circle? Could you ever get like an oval? Or could you ever get, well, you could never get something with straight sides, right? Because it's circle all the way around. But could you get an oval instead of a circle? Next time you're at the store, if your mom or if your family is willing to let you get a cantaloupe or a honeydew or a watermelon or something that is spherical, try slicing it different ways. You know, slice off a little bit over here and then some over here. See if you can make a shape other than a circle with one straight cut. No zigzag cuts. Not making two cuts. Just one straight cut. Can you make a shape that's not a circle? If you can, let me know in the comments down below. I don't think it's possible. All right, cool. Next, let's look at F. Let's look at the last piece. What is the blue three-dimensional shape? It is a cube. It's hard to see behind that yellow plane, but you can see if we connect it all, it is indeed making a cube. And now, what are they doing? They're not cutting along, like, perfectly along the diagonal. They're going almost across the diagonal, if we think of, like, the end of this box. They're not cutting it perfectly from end to end. They're cutting it on the edge, like before the corner. They're cutting it somewhere like here. And then when they go through, they're cutting even closer to the corner on the other side. So they're cutting not super close to the corner and then closer to the corner as they get further down through their cut. So what is this purple shape that they have highlighted? What is this shape? That's not a rectangle because these two sides on like the top and bottom aren't congruent. What is this shape? Do you remember from chapter 7? This is a trapezoid. Whoa, you can make a trapezoid out of a cube? Yes. And I encourage you again, when you're done cutting the sphere of your watermelon, cut the watermelon into a cube and try this. Try and see if you can make a trapezoid as well, because you can. You just have to start closer to the center and then for the beginning of your cut, and then get closer to the edge of the cube for as you finish the cut. Remember, one straight cut, no zigzags. All right, let us check and make sure that we were correct. We have hexagon, triangle, rectangle, circle, circle, trapezoid. That sounds just like what we said. So very good. Good job. And we are moving on to our last concept for today. This one is pretty quick because all we're doing is we're spinning a shape around an axis. So I'm taking something and we're spinning it around a line of some sort. And we're going to call it a solid of revolution, because you made it by revolving a shape or turning, rotating a shape around an axis. That axis we call the axis of revolution. And in Calculus 2, in integral calculus, you will define your axis of revolution to be the x-axis, and that means that you're spinning your shape this way, or the y-axis, and that means you're spinning your shape this way. So the axis of revolution, important to differentiate, because this gonna make a different shape than this. Okay, cool. So here is a little example that they're giving you. If you take a rectangle, this is a rectangle, and you rotate it, you turn it around this line, you spin it around, when you get all the way back where you started, you have a cylinder. Huh, cool. If we could print, if I could bring in my 3D printer and show you in class, yeah, it's like you're spinning this rectangle around this line. So when you complete it, you have a circle on the top, because you've gone around this line. You have a circle on the top and you have a circle on the bottom, which is what you get over here. But you still have straight sides on the outside because the rectangle you started with had a straight side. So it has to do with the shape that you start with. What shape will you end with? So let's try some more on the next slide. So first, we have, let's see, 9, 9, 4, 4. Those are matching, and we are given a right angle right here. So that means that this is a rectangle. And hey, we just talked about if we rotate a rectangle around an axis, what shape should we get? Notice that this axis of revolution is horizontal, whereas on the last slide it was vertical. It doesn't matter. It'll still be the same shape. Let me show you. If we take this top left point and we rotate it around the axis of revolution, so we go around in a circle, and then I'm going to take the other corner of the point and we're going to rotate it around in a circle, going down just as far as you came up. So like this length should be the same as this length, if that makes sense. And then you'll notice if you connect these sides with a straight side, just like you have a straight side up here, you will get a cylinder, just like we did on the last slide. Are these 9s and 4s important? They actually kind of are. And especially when we get into volume and surface area of cylinders, these numbers are going to be incredibly important. 9, this is the height of your cylinder. This is how tall, if the cylinder were standing up on its end, how tall the cylinder is, or how long the cylinder is. So you can call it height, you can call it length, whatever you want to call it. I'll call it height. The height is 9, and this 4, that 4 is the radius of the circle that's on the edge of either end of the cylinder. So we have a radius of 4 for the base. So this is a cylinder with height 9 and radius 4. All right, in part B, this is not a rectangle. We've only talked about rectangles up until this point, but triangles are still cool. So you'll notice that this yellow shape is a triangle. It is a right triangle, as they've told us, so that's cool. And it's actually very important that that's a right triangle, because if it weren't a right angle, if it were acute, well, when we rotate this around, we're not going to have a flat bottom. But because this is perpendicular, when you rotate this bold line I put here, when you rotate that, you will get a flat bottom. Because it is perpendicular to vertical, that means that it's perfectly horizontal. So when you spin something perfectly horizontal, it'll stay horizontal the whole time. So that's very important. If you had like a shape that was, if you had this triangle instead, when you rotate it around, you're going to get a very different shape. You're going to get like a top. You know those tops that you used to spin? Like you'd spin them and then they'd spin on the ground? You'd get more of a top shape. But because this is perpendicular, when we take this point and wrap it around the, that wasn't a very good circle. When we wrap it around this axis, we have a slanted edge over here. We're going to have a slanted edge over here. What shape is that? Although some of you might be thinking, Miss Dodge, you didn't rotate this point around the axis, but that point is on the axis, right? If I ask you to rotate the tip of this pen around the pen, well, but it's on the pen. It's not moving. Even if I rotate the pen, the tip ain't moving. It's in the same spot. So the point up at the top stays in the exact same place, and we have a cone. We have a cone with, notice that 5 is labeling how tall the original triangle was. So this is a cone with height 5. And what does that 2 mean? The 2 is the radius of your base. And that's going to be very important. The radius of your base is going to become very important as we start doing surface area and volume of shapes. Awesome. Let's check and make sure that we were correct. We have cylinder with a height of 9 and a radius of 4. Very good. And a cone with a height of 5 and a base radius of 2. They call it base radius instead of radius. That's okay. We know it's the radius of the base. Alrighty, very good for us. Okay, that is all I have for you today. So now is a great time to reflect on the learning target and the success criteria, see how you're feeling. If you totally, completely understand everything, you're like, easy peasy, give me any shape, I'll tell you the cross section, I'll classify it for you, I'll rotate it around, well, you can only rotate two-dimensional objects around an axis. You could tell me what it looks like. Awesome. Then you are a 3, and you are good to finish your homework and help others, teach your parents what you've learned, teach your family, teach your younger siblings. That's awesome. If you're like, hey, I think I get what you mean, I'm not 100% sure what's going on, but like, I get the idea, then you're a 2, and you're gonna start on the homework or start on some practice problems I'll show you below and see how you feel. If you get stuck, that is totally okay, but you're gonna work through it by asking questions from a classmate or a teacher. So you're going to start with the homework and ask for help if you get stuck. And if you are super horribly confused, you have no idea what's going on, what the heck is a cross-section, I can't picture any of this in my head, I don't know what's going on, that's okay. You're a 1, 1s are cool, 1 is, number 1. But you should ask a teacher, talk to a teacher, see if they can show you some visual images, actually take a Kleenex box and chop the edge off or something. Could be very, very helpful. So you are going to ask questions if you are a 1. Alrighty, awesome, awesome. Here are those practice problems I was mentioning before. For my students, these are, some of these will be in big ideas. But if you're watching, you can still try some of these on your own. There are lots of them, so you can get tons of practice. Woohoo! All right, your launch for today comes from Henry Ford, and he says, obstacles are those frightful things you see when you take your eyes off your goals. Obstacles don't exist if you keep your eye on the prize. If you pay attention to your goals, you're just chugging towards your goals, nothing can stop you. An obstacle? No, that's just a decision to be made. I decide, no, keep on going with my goals. Another decision to be made? Okay, I'm gonna do this. Keep moving with your goals. Don't let anything get in your way. If you really want something, no excuses. No obstacles, no excuses. Keep your eye on the prize, and you can reach your goals. With determination and hard work, you can reach every goal that you set for yourself. So, that is my launch for you today. Take it with you as you go throughout your day. Have a wonderful rest of your day, and thanks for being here. Thanks for watching. Bye!